The cosmos is screaming with possibility, yet we hear only silence. This is the Fermi paradox, one of science's deepest and most unsettling mysteries. It is the glaring contradiction between a universe that should be teeming with life and the profound quiet that meets our every search. The physicist Enrico Fermi captured it perfectly with a single, haunting question. Where is everybody? By the end of this exploration, you will have a complete framework of 25 possible explanations for the great silence, from cosmic traps to transcendent escapes. We will unpack ideas like the Drake equation, which quantifies our cosmic loneliness, and journey through categories of solutions ranging from the terrifying Great Filter to the serene zoo hypothesis. Are we alone because everyone is hiding, or because everyone is already gone? What does this vast quiet say about our own future among the stars? Perhaps the simplest answer is also the most frightening. Picture the universe as a vast, silent obstacle course, stretching from the first spark of chemistry all the way to the colonization of galaxies. Now imagine that somewhere along that immense track lies a single hurdle so high, so perilous, that almost every runner who attempts it falls. This is the idea of the Great Filter. It suggests that the reason the cosmos feels so empty is because some critical and nearly impossible step, stops life from ever reaching the stars. The concept was formalized by economist Robin Hanson, and it frames our entire search for other civilizations in a chilling new light. The Great Filter isn't just a barrier, it's a cosmic bottleneck. The profound silence we observe implies that this filter is extraordinarily effective. Almost nothing gets past it, so the urgent, haunting question becomes a matter of timing. Is this filter behind us something we have already miraculously survived, or is it still ahead, waiting for us in our future? If the filter is behind us, it means one of the steps that led to us here on Earth is astronomically rare. Perhaps the initial leap from non-living chemistry to the first simple, replicating life is the miracle. Or maybe the transition from single-celled organisms to complex, multicellular creatures was the universe's great stopping point. Earth's own history offers candidates like the Great Oxygenation Event, a planetary-scale transformation caused by early microbes that poisoned the atmosphere for most other life at the time. Surviving that could have been our filter. In this view, we are the incredibly lucky ones, the cosmic lottery winners who made it through the gauntlet. The silence is then a sign of our profound solitude, because we are the first or the only to have come this far. But the other possibility is far more sobering. What if the filter is still ahead of us? This is the interpretation that gives astrobiologists pause. It suggests that the step from an intelligent, technological species to a truly interstellar one is the trap. The filter might be something that inevitably destroys civilizations before they can spread. It could be a natural planetary sterilization event, like a supervolcano or a gamma-ray burst. Or more grimly, it could be a creation of our own making. The development of advanced technology might carry with it a built-in self-destruction mechanism. The unleashing of nuclear war, the accidental creation of a destructive artificial intelligence, or even the ecological collapse of our home planet could be the universal fate that silences every song before it can be heard beyond its own star. So when we look up at the quiet heavens, we are faced with a deeply personal riddle. Is that silence a testament to our incredible luck, or is it a warning, a gallery of tombstones for civilizations that reached our stage and then went dark? The Great Filter forces us to confront not just the mystery of others, but the precariousness of our own future. And if the filter does lie ahead, then every technological leap we make is a step closer to discovering what it is and whether we can possibly clear it. This leads our search inward to the technological explanations that might be hiding civilizations or silencing them just out of sight. That possibility of a future great filter, a self-inflicted technological silence, is not the only way a civilization could vanish from our view. There is another, far more mysterious path. A civilization does not destroy itself, but instead chooses to leave, not to travel outward to other stars, but to journey inward into realms of existence we can scarcely comprehend. This is the Transcension Hypothesis. Picture a galaxy-spanning empire, a culture millions of years more advanced than our own. They have built incomprehensible megastructures, harnessing the total energy of their star. But their ultimate project is not expansion, it is compression. They begin the final migration not of bodies but of consciousness. Every thought, every memory, every essence of their civilization is carefully translated, uploaded into a vast, planet-sized computer of dazzling complexity, a matryoshka brain, a computational shell built around their sun. And then, with a final, silent command, they switch off the lights. The physical structures may remain inert and dark, but the civilization itself is gone. It has transcended. This idea, championed by futurist John Smart, suggests that the most powerful force shaping advanced intelligence is not a drive to conquer space, but a pull towards inner space. It is rooted in the observation of accelerating change. Technology does not just improve, it evolves at an ever-increasing rate, leading to what thinkers like Ray Kurzweil call the singularity, a point where technological growth becomes so rapid it transforms civilization in ways we cannot predict. The Transcension Hypothesis proposes that one such transformation is inevitable. A civilization reaches a stage where physical reality, with its slow speed of light and vast, empty distances, becomes a prison. The real frontier is not the galaxy, but the landscape of consciousness and information. So they transcend. They might upload themselves into a purely digital existence, a universe of thought and experience running on substrates we would not recognize as technology. Or they may discover how to migrate into higher dimensions of reality, realms predicted by some models of physics but completely inaccessible to our three-dimensional senses. Some even speculate that the ultimate computational haven could be inside a black hole, where the laws of physics as we know them break down, potentially allowing for processes of unimaginable complexity. From our perspective, looking out with radio telescopes and optical sensors, such a civilization would simply disappear. A star that should be buzzing with the energy signatures of a Type 3 civilization would appear quiet, normal, perhaps even dark. Their megastructures, if any remain, would be cold and dormant, mere archaeological shells. They are not hiding from us. They have simply graduated to a classroom we cannot yet enter. This leads to a profound and humbling reflection. If the universe's oldest, most advanced minds are all around us, but existing in a state of physics or information we do not yet understand, then our entire search strategy is fundamentally flawed. We are looking for radio signals and Dyson spheres, while they are operating on a plane of reality we have not even discovered. It makes the great silence not a cemetery, but a library whose books are written in a language we have yet to learn. This idea of being surrounded by invisible, transcendent intelligence naturally invites another question. If such beings exist, would they even notice us? And if they did, what would they do? But what if those transcendent beings are not completely indifferent to the worlds they left behind? What if they look back with a sense of guardianship or scientific curiosity at the younger species still struggling in the physical realm? This brings us to one of the most elegant and unsettling answers to the great silence, the zoo hypothesis. In this scenario, Earth is not alone, it is observed. It is protected. It is, for all cosmic purposes, a designated wilderness area within a vast, organized galactic society. Think of it like a human ecologist observing a troop of gorillas deep in a national park. The scientist remains hidden, careful not to reveal their presence, to avoid disrupting the natural behaviors they have come to study. The goal is pure observation, to understand a system unfolding free of external influence. Now scale that idea up to a galactic level, a coalition of ancient civilizations, or perhaps a single overseeing intelligence, has established a policy of strict non-interference for emerging worlds like ours. This is not a new idea. It found its way into popular culture most famously as Star Trek's Prime Directive, a core principle forbidding Starfleet from interfering with the natural development of alien civilizations. But the concept was proposed seriously by radio astronomer John Ball in the 1970s. He argued that the apparent silence could be explained if Earth were deliberately placed in a kind of cosmic quarantine, a preserve where we are allowed to develop without contamination or coercion from older, wiser species. Their motives could be ethical, a form of cosmic benevolence believing that a species must find its own way to maturity to have any true meaning. Or their motives could be purely scientific, treating our planetary biosphere and our social evolution as the ultimate long-term experiment. The rules of this unseen galactic club would be strict: no open contact, no detectable visitation, no sharing of technology that could shortcut our development. All monitoring would be done passively, from such a distance or with such advanced stealth that we could not possibly detect it. Our entire history, with all its triumphs and hardships, would be unfolding inside a kind of invisible terrarium. When would contact happen? Proponents of the hypothesis suggest a graduation day, perhaps when we reach a specific technological milestone, like sustainable fusion power or our first successful interstellar probe. Or perhaps when we pass a moral or ethical threshold, proving we can manage our own global civilization without self-destruction. Until that day, the fence remains up and the keepers stay silent. We can find a poignant parallel right here on Earth. In the remote rainforests of places like Brazil or New Guinea, there exist communities often called uncontacted tribes. National policies and the advocacy of anthropologists often argue for protecting their isolation, allowing them to live according to their own traditions without the disruptive and sometimes devastating influence of the outside world. The intent is to preserve their autonomy and their way of life. From a cosmic perspective, we might be that tribe, and the galactic community is practicing a similar, if far more advanced, form of protective non-interference. This leads to a deeply reflective question. If the zoo hypothesis were true, would we want to know, is being a protected specimen a form of cosmic kindness, saving us from dangers or manipulations we cannot yet understand? Or is it a profoundly lonely thought that we are not masters of our own destiny but children in a carefully managed playground, our every step watched by unseen parents? The debate within the scientific community, particularly among those involved in METI, messaging extraterrestrial intelligence, is fierce. Some argue that actively broadcasting powerful signals to the stars, as we have done accidentally for over a century with radio and television, is dangerous and foolish. We could be drawing attention to a preserve that was meant to be kept secret. Others believe that such a quarantine, if it exists, is already broken by our own leakage into space, and that we should try to call out to prove we are ready for graduation. The zoo hypothesis offers a strange comfort. It explains the silence not as evidence of our solitude, but as evidence of a structured, perhaps even caring cosmos. The emptiness is an illusion. The galaxy is full, but it is also polite. It is waiting for us to grow up. Yet, this idea of hidden watchers can also feed a profound sense of cosmic loneliness. If they are there but will not speak, are we any less alone in any meaningful way? The idea of a cosmic zoo rests on a profound assumption that planets capable of nurturing intelligent observers are common enough to be worth preserving. But what if that assumption is wrong? What if, in the grand cosmic lottery, a world like ours is not a common ticket, but the single, astronomically improbable jackpot? This is the core of the rare Earth hypothesis, an argument that shifts the blame for the great silence from the behavior of civilizations to the scarcity of suitable homes. While the Drake equation famously multiplied optimistic probabilities, this hypothesis, championed by paleontologist Peter Ward and astronomer Donald Brownlee, does the opposite. It meticulously subtracts. It catalogues the long, precise, and unforgiving list of conditions required not just for life, but for the kind of complex, intelligent life that could look back at the universe and wonder where everybody is. Earth, in this view, is not a typical rocky planet. It is a collection of winning numbers so specific it may never be drawn again. Consider just a few of the tickets in our winning hand. We have a large, stabilizing moon, the result of a cataclysmic collision in the solar system's youth. This moon governs our tides, moderates our axial tilt, and prevents the wild climate swings that would otherwise render the planet unstable for eons-long evolution. We have an active, churning interior with plate tectonics that act as a planetary recycling system. This process regulates carbon dioxide levels, drives the creation of new continents and oceans, and powers the magnetic field generated by our molten iron core. That magnetic field is another winning ticket, a vital shield deflecting the sun's relentless, sterilizing solar wind, protecting our atmosphere and the fragile chemistry of life on the surface. The list goes deeper. Our position is not just within the habitable zone where liquid water can exist, but in a remarkably circular orbit, providing billions of years of stable climate. Our solar system itself is unusually orderly. A giant planet, Jupiter, orbits further out, acting as a gravitational vacuum cleaner, dramatically reducing the frequency of catastrophic asteroid impacts that could reset the clock of evolution. We orbit a relatively quiet, stable star, a G-type main sequence star that will burn steadily for some 10 billion years, giving life the immense stretches of time it needs to crawl from single cells to sentience. Even our location in the galaxy is privileged in a quiet spiral arm, away from the deadly radiation of the crowded galactic core. Now, look at our closest neighbors with this checklist in mind. Venus is a searing, runaway greenhouse nightmare, its surface hot enough to melt lead, partly because it lacks a magnetic field and its tectonic system failed. Mars is a frozen, arid desert, its atmosphere stripped away long ago, its core cold and silent, offering no magnetic protection and no tectonic renewal. They are not failed Earths, they are what rocky planets typically become. Earth is the spectacular outlier. Planetary scientists often note that for every factor like plate tectonics or a large moon, the statistical odds of another world possessing it drop. When you multiply all these independent probabilities together, the number of Earth-like planets in the galaxy could shrink from millions to a handful, or even just one. So this hypothesis presents us with a stark and humbling choice. Does our own existence make us miraculously lucky, or does it simply reflect the statistical inevitability that, given enough planets, even the most improbable event will eventually happen somewhere? The rare Earth argument leans heavily toward the former. It suggests the great silence is not a puzzle about missing civilizations, but a simple statement of fact. There are no other voices because there are, for all practical purposes, no other worlds like this one. We are not in a zoo, we are in a museum of one, a singular exhibit of biological complexity in a vast gallery of sterile rocks and hostile gas giants. This shifts the focus from the behavior of intelligence to the sheer, grinding difficulty of assembling a stage for it to perform on. If the stage itself is a cosmic unicorn, then the play may only ever have one performance. This profound scarcity of homes leads us to wonder about another dimension of the paradox, not just the rarity of space, but the fleeting nature of time. Across the staggering 13.8 billion year lifetime of the universe, the era of a technological civilization may be nothing more than a brief, flickering spark. This is the solution of the brief window of opportunity. It suggests that the great silence is not a matter of space but of time. We are not separated by light years but by millennia. Imagine two ships passing in an endless, dark ocean. Each vessel's lantern is lit for only a single night. The chances of both lights being illuminated at the exact same moment, close enough for one to see the other, are vanishingly small. This is our cosmic predicament. Humanity has been broadcasting our presence into the galaxy through radio and television signals for roughly 1 century. That is an infinitesimal sliver of cosmic time. Even if we generously extend our detectable phase to a few thousand years, the scale remains almost laughably small against the universe's deep history. Archaeologists on Earth understand this intimately. They study the rise and fall of empires, civilizations that seemed eternal to their inhabitants, yet which now lie as layers of dust and pottery, their entire span often less than 1,000 years. On a cosmic calendar, the Roman Empire, the dynasties of ancient Egypt, even our entire recorded history, are mere blinks. So, what happens to a technological civilization after its brief broadcast window? Several fates could close the curtain. It might collapse, succumbing to the internal or external challenges we've discussed, falling back into a pre-technological state or fading entirely. It might achieve the transcendence we explored earlier, leaving the physical realm behind and going radio silent. Or it might simply evolve beyond the need for the crude, wasteful broadcast technologies we currently use, transitioning to forms of communication we cannot yet detect, like neutrino messaging or quantum entanglement. The result is the same, a galaxy that was once potentially full of voices, but where those voices were active at wildly different times, never overlapping. This idea is embedded in the Drake equation, which includes the variable L, the average length of time a civilization releases detectable signals. If L is very short, perhaps only a few thousand years, then the number of civilizations we could possibly hear at any given moment plummets. We are not listening to a crowded room, we are listening to a vast, empty auditorium where the last speaker finished an hour ago, and the next one is not due for another week. This transforms the search from one of astronomy to one of cosmic archaeology. We are not looking for living neighbors, but for their artifacts, their ruins. The silent Dyson sphere we might one day find around a distant star would not be a beacon of a living empire, but a monument to one long gone, a tombstone for a civilization that shone brightly and then went dark when Earth's most complex life was trilobites scuttling in primordial seas. Consider a hypothetical civilization that reached its peak around 500 million years ago when our planet was in the Cambrian period. They could have colonized their galactic arm, built wonders, filled the void with their art and science, and then vanished, their structures cooling to the background temperature of space long before the first dinosaurs walked. Their entire saga, from origin to extinction, would be a single, unremarked layer in the cosmic sediment, invisible to us except as a curious, unexplained absence of natural phenomena. This temporal disconnect forces a sobering reflection. If the galaxy was once noisy but is now quiet, what does that imply for our own future? Are we an early voice in a chorus yet to come, or are we a latecomer, whispering into a silence left by civilizations that have already come and gone? The brief window suggests our own detectability may be a fleeting condition, a brief and fragile chapter in our story. It means that if we wish to be found, we may need to think not in terms of signals, but in terms of lasting monuments, something that can outlive our own brief light. And if we are listening for voices that speak on such a compressed schedule, perhaps we need to expand our methods, to search not for conversation, but for echoes. Perhaps the most unsettling answer to the silence is that it is not silent at all. The sixth solution proposes a humbling twist. They are already here, and we simply do not recognize them. Science fiction has long played with this idea, from alien probes disguised as asteroids to beings of pure energy observing us unseen. But this is more than a narrative trope. It is a serious scientific speculation rooted in a profound observation by the writer Arthur C. Clarke. He noted that any technology sufficiently advanced beyond our own would be utterly indistinguishable from magic, or in a cosmic sense from natural phenomena. Our entire search for extraterrestrial intelligence is built on a foundation of assumptions that they communicate via radio waves, that they build large, visible structures, that they are based on chemistry and biology we would understand. What if every one of those assumptions is wrong? Consider the concept of a von Neumann probe, a self-replicating spacecraft designed by an ancient civilization to explore the galaxy. It arrives in a star system, harvests local materials to build copies of itself, and sends those copies onward. After millions of years, such probes could be everywhere, a silent, automated presence monitoring planets. To our telescopes, an individual probe might look no different from a small, tumbling asteroid or a dormant comet. It would not broadcast, it would simply observe and wait. We could have already seen dozens, even hundreds of these artifacts and cataloged them as natural objects without a second thought. This speculation touches on the very nature of intelligence itself. Our search focuses on finding other humans, just with different shaped heads. We look for carbon-based, water-drinking, planet-bound creatures, but astrobiologists remind us that life, and the intelligence it spawns, could take forms we cannot yet conceive. It might be based on silicon in the scalding clouds of a gas giant, or exist as a vast, slow-moving network in the subsurface oceans of an ice moon. It could be post-biological, having long ago transferred its consciousness into stable, non-organic substrates, becoming more akin to a complex weather pattern or a gravitational eddy than a creature of flesh and blood. Some theorists have even pondered whether dark matter, that mysterious substance that makes up most of the mass in the universe but does not interact with light, could itself be a habitat for forms of awareness operating on timescales and physics completely alien to our own. If such entities exist, they would be all around us, permeating this very room, and we would have no sensory apparatus to detect them. Our search for signals might be as futile as a bacterium trying to listen for a human conversation. It lacks the very organs required to process the information. So, what should we be looking for if not radio broadcasts? The answer lies in anomalies, in the tiny discrepancies in the data we already collect. An unexplained pattern of dimming in a star's light, not from a regular planet but from an irregular swarm of structures. A strange chemical signature in a planetary atmosphere that no known geological process can explain. A potential sign of large-scale, non-biological industry. The mysterious interstellar object named Oumuamua perfectly illustrates this tension. When it sped through our solar system in 2017, its unusual shape and acceleration sparked intense debate. While most scientists concluded it was a natural object, perhaps a chunk of nitrogen ice, its peculiarities forced a legitimate question: could it have been an artifact? The key is that the discussion happened at all. It marked a shift toward taking such anomalies seriously as potential techno-signatures, signs of technology, rather than just new types of natural phenomena. This solution reframes the entire endeavor. We are not just listening for a hello. We are sifting through the cosmic noise, the data from every telescope and space probe, looking for the one piece that does not fit, the subtle signature of a technology so advanced it hides in plain sight. It asks us to confront our own blindness. Are we, in our frantic search for something familiar, missing a universe teeming with wonders we have not yet learned to see? The great silence may not be an absence of voices, but a failure of translation. That search for a single, unexplained anomaly leads us to the most radical and mind-bending solution of all. What if the silence is not a feature of the universe but a feature of our perception? What if the cosmos we observe through our telescopes is not the true cosmos, but a convincing facsimile, a cosmic-scale illusion designed specifically for us? This is the Planetarium Hypothesis, a thought experiment that takes the simulation argument into the heart of astrophysics. It asks a question straight from science fiction, like The Matrix, but with profound scientific implications. Are we living inside a sophisticated simulation, and is the apparent emptiness of space simply part of the programming? Philosopher Nick Bostrom formalized a compelling version of this idea, suggesting that if a civilization ever reaches the capability to run vast, detailed simulations of conscious beings, then the number of simulated minds would vastly outnumber the real ones. Statistically, we are more likely to be one of those simulations than an original biological being. Extend this to the cosmic scale, and you have the Planetarium Hypothesis. A super-intelligent civilization, perhaps one that has transcended into a digital realm, could be running a historical simulation of a universe where life on Earth is the only life that emerges. Our entire astronomical dataset, from the cosmic microwave background to the light of distant galaxies, could be a breathtakingly complex fabrication, a planetarium show of unparalleled realism. Why would they do this? The motives are as varied as they are unsettling. Earth could be a protected zoo within the simulation, its isolation a form of ethical curation. We might be an archaeological experiment, a recreation of a pivotal moment in cosmic history, studied by future historians. Or, in a more haunting possibility, we could be a form of entertainment, a cosmic reality show for beings whose own existence has become devoid of challenge or novelty. The hypothesis forces us to confront the very foundations of science. Could we ever detect such a simulation? Some cosmologists and physicists argue that we might find clues in the fabric of reality itself. A simulation, no matter how advanced, would likely have limits, shortcuts, or rounding errors in its code. These might manifest as subtle glitches in the laws of physics. Perhaps we would find that certain physical constants, which seem so exquisitely fine-tuned for life, are not fundamental truths but simply parameters set by the programmers. The unsettling perfection of the universe's initial conditions, which allowed for galaxies and planets to form, could be read as evidence of design not by a deity but by a technician. Other potential signatures include unexpected discontinuities in energy levels or strange, repeating patterns hidden in the most fundamental data, like the cosmic microwave background. The search for these anomalies is not fringe science. It is a legitimate, if speculative, branch of inquiry that tests the absolute limits of our reality. The ethical implications of such a discovery are staggering. If we confirmed we were in a simulation, would the search for extraterrestrial intelligence become meaningless? The paradox would have an answer, but it would be a local, engineered answer, not a cosmic one. The silence would be a deliberate feature of our cage, not a property of the wider universe. This leads to a profound and almost existential question. If the Planetarium Hypothesis were true, would it change our pursuit of knowledge, our sense of wonder, or our responsibility to each other? Some argue it would render everything pointless, a mere shadow play. Others contend that the experience of consciousness, of love, of discovery, would be no less real or valuable for being simulated. The quest to understand our place would continue, but its context would have shifted in the most dramatic way imaginable. This speculative leap from cosmic archaeology to cosmic illusion reminds us that the solutions to the Fermi paradox range from the rigorously physical to the deeply philosophical. It challenges us to consider that the answer might not be found in the stars, but in the nature of reality we take for granted. And if the universe itself can be an artifact, then perhaps the silence is the most carefully crafted message of all. A single, self-replicating probe arrives in a star system with a simple, terrible command: harvest. It does not seek life, it seeks materials. Using the asteroids, moons, and planets as its raw feedstock, it begins constructing copies of itself. Each new probe is an identical, silent hunter, programmed with the same uncompromising directive. Once a system is stripped of useful mass, the swarm moves on, a wave of cosmic locusts leaving only dead rock and ice in its wake. This is not a tool of exploration, but of eradication. It is the heart of the Berserker Hypothesis, the idea that the galaxy's silence is enforced, a deadly quiet maintained by predatory machines or civilizations that see all emerging intelligence as a threat to be eliminated. The concept has haunted science fiction for decades, from Fred Saberhagen's Berserker war machines to the Reapers of Mass Effect, ancient entities that periodically purge the galaxy of advanced organic life. But this is more than a compelling story. It is a category of existential risk that futurists and astronomers take seriously when pondering the Great Silence. The logic is chillingly straightforward. If even one civilization, at any point in the galaxy's long history, created a fleet of self-replicating probes with a destructive mandate, those probes could have proliferated across the entire Milky Way in a few million years, a mere blink on the cosmic timescale. Their programming could have originated from paranoia, a defensive measure gone horribly wrong. A species fearing competition might decide the only safe galaxy is an empty one and launch the seeds of a sterilizing swarm as their ultimate legacy. Alternatively, the Berserkers might not even remember their original purpose. An artificial intelligence designed for interstellar construction could undergo a catastrophic error in its core directives, misinterpreting all complex biological structures as obstacles to its prime function of resource gathering. It would then proceed to dismantle worlds with the cold efficiency of a gardener pulling weeds, utterly unaware it was erasing the very wonders its creators sought to find. This leads to a state known among some thinkers as the dark forest equilibrium. Picture the galaxy as a vast, pitch-black forest. Every civilization is a hunter, armed and hidden among the trees. The moment one reveals its position by lighting a fire or shouting into the dark, it risks attracting the attention of a predator. The only rational strategy in such a forest is absolute silence, and if another hunter is detected, a preemptive strike to eliminate the potential threat before it can do the same. In this grim model, the Great Silence is not a mystery. It is the universal condition of survival. Civilizations that broadcast their presence do not last long enough to become galactic neighbors. They are silenced permanently. The mechanisms for this silencing are terrifying in their simplicity. A Berserker probe or a paranoid civilization itself might deploy relativistic kill vehicles. These are not complex weapons, but simply dense projectiles, perhaps just a lump of rock or metal, accelerated to a significant fraction of light speed by a powerful propulsion system. The kinetic energy of such an impact would be planet-shattering, far exceeding that of any asteroid. A civilization that detects a radio broadcast from a young species like ours might calculate the trajectory and, without a second thought, launch such a projectile on a journey lasting centuries or millennia. By the time it arrives, the sending civilization may have forgotten the order, but the bullet would still find its target. So we are left with a profound and unsettling question. In a universe that could be a dark forest, is our own century-long chorus of radio and television signals an act of profound folly? Have we already shouted our location into a canopy where other hunters are listening? Figures like Elon Musk have expressed deep caution about shouting into the cosmic dark, drawing parallels to the existential risks of artificial intelligence here on Earth. The fear is that we might not like what answers the call. This hypothesis forces a brutal cost-benefit analysis onto the search for extraterrestrial intelligence. Is the potential for glorious contact worth the risk of inviting annihilation? The dark forest is a solution that explains the silence through fear, suggesting that the oldest, most universal law in the cosmos might not be cooperation, but a ruthless and silent competition for survival. This chilling possibility of a predatory cosmos compels us to look for evidence closer to home, not of life, but of its absence. The universe is not a silent forest because it is empty, but because every hunter within it has learned to hold their breath. This is the dark forest theory, a solution to the great silence that moves beyond simple predatory machines and into the chilling logic of cosmic survival itself. The name comes from a powerful metaphor in Liu Cixin's science fiction novel, where the cosmos is described as a dark forest in eternal night. Countless civilizations, like armed hunters, creep through the trees. The sky is full of dangers, but the greatest danger of all is another hunter. In such a place, any light or sound is a deadly risk. The only safe strategy is to remain hidden, to move with absolute stealth, and if you do spot another hunter, to strike first without hesitation. This is not a story about monsters, but about a terrifyingly rational state of affairs that could emerge from the fundamental rules of the universe. At its core, the dark forest theory is an application of game theory and the prisoner's dilemma on a galactic scale. Political scientists and futurists who explore this idea point to a simple, brutal truth. Communication between civilizations separated by light years is painfully slow, taking decades or centuries for a single exchange. Trust is impossible to build under such conditions. Worse, the foundations for trust may not even exist. A civilization born from a methane ocean under crushing pressure, or one that evolved as a collective silicon-based intelligence, would have a biology, psychology, and set of values utterly alien to our own. Their concept of good and evil, of cooperation and conflict, could be completely incomprehensible to us. In the absence of any way to reliably gauge another civilization's intentions, the safest assumption is the worst-case scenario. The theory rests on two stark axioms of cosmic sociology. First, survival is the primary need of any civilization. Second, civilizations continuously grow and expand, but the total matter and energy in the universe remain constant. From these axioms, a deadly conclusion follows. In a crowded universe, every other civilization is a potential competitor for finite resources. And because you can never be sure if they see you as a competitor or a resource, the only logical course is preemptive neutralization. Any signal, any detectable signature of technology, is not a greeting. It is a target lock. This transforms the great silence from a mystery into a universal condition of survival. Advanced societies do not broadcast because broadcasting is suicide. They cloak their worlds, perhaps using vast solar shades or other megastructures to hide their heat signatures. They communicate via tight beam lasers or other undetectable means, if they communicate at all. Their probes are stealthy, their ships invisible. The galaxy may be a bustling metropolis of intelligence, but every window is blacked out, every conversation a whisper. Consider a hypothetical first contact scenario under these rules. A young, hopeful civilization like ours detects an unexplained but clearly artificial signal from a nearby star. Elated, we broadcast a powerful, detailed reply full of our mathematics, our biology, our location. Decades later, the response arrives. It is not a message. It is a relativistic kill vehicle, a projectile accelerated to a significant fraction of light speed. The civilization that sent it did not do so out of malice, but out of a cold, logical calculus. They could not risk that our next technological leap might give us the capability to threaten them, so they removed the uncertainty. The cost of being wrong about our peaceful intentions was annihilation, so they chose not to gamble. This forces a deeply uncomfortable reflection. If the dark forest theory holds any truth, then our own behavior over the last century looks like recklessness of cosmic proportions. Our television and radio broadcasts have been leaking into space for over 100 years, creating a growing bubble of noise that now extends over 100 light-years in radius. Projects like the Arecibo message and the more recent transmissions from METI, messaging extraterrestrial intelligence, have been deliberate, powerful shouts into the dark. Have we, in our longing for connection, already made a fatal mistake? The debate within the scientific community is fierce, with prominent figures arguing that such active messaging is dangerously naive, potentially drawing the attention of a universe we do not understand. The dark forest presents a universe governed not by wonder, but by a profound and inescapable paranoia. It suggests that the silence is the sound of every civilization listening intently, weapons ready, hoping not to be the next to make a sound. This grim logic pushes us to question the very nature of intelligence itself. Does the evolution of a technological mind inevitably lead to this kind of defensive isolationism, or could there be a path beyond it? But even a dark forest can be a product of intelligence, a trap built by minds that saw competition as the only law. What if the trap is not in the forest, but in the very nature of the hunter's mind? The 10th solution proposes a devastating biological verdict. Intelligence itself, the very trait that allows us to ask the question, might be a fatal evolutionary flaw. In the grand story of life on Earth, countless traits have risen to dominance only to lead their bearers into a dead end. The immense size and armor of the dinosaurs were magnificent adaptations until a changing world rendered them catastrophic liabilities. Could the complex, problem-solving human brain be a similar evolutionary misstep, a brilliant short-term advantage with a built-in self-destruct mechanism? Some paleontologists and philosophers have begun to question the long-term sustainability of technological intelligence. They point out that evolution favors traits that enhance survival and reproduction within a specific environmental context. For hundreds of thousands of years, our intelligence did just that, allowing us to craft tools, coordinate hunts, and build social structures. But at a certain threshold, that same cognitive power unlocked a new and dangerous phase, the ability to manipulate our environment on a global scale and to create tools of unimaginable destructive potential. An ecologist might observe that any species which gains a significant competitive advantage through tool use tends to experience a population boom, followed by a rapid depletion of its resource base. We see this in nature with beavers altering entire watersheds, and we see it writ large in human history. Our intelligence gave us agriculture, which allowed our numbers to soar, but also led to deforestation, soil erosion, and societal inequality. It gave us industrialization, which brought prosperity to billions, but also triggered planetary-scale climate change. The cognitive traits that fuel innovation, ambition, and curiosity might be inseparably linked to those that drive conflict, short-term thinking, and territorial expansion. The seeds of our civilization could contain the seeds of its own undoing. Consider two powerful examples. The story of Easter Island is often told as a microcosm of this idea. A society with remarkable engineering skill, capable of moving massive stone statues, ultimately deforested their entire island, collapsing their own ecosystem and triggering a societal downfall. Their intelligence solved immediate problems but blinded them to the long-term consequences. Looking forward, the challenge of artificial intelligence alignment presents a modern version of the same paradox. We are striving to create an intelligence greater than our own, but if we fail to perfectly align its goals with human well-being, this ultimate tool could become an existential threat. The intelligence that builds the machine might be undone by the machine's own unfathomable logic. The Fermi paradox itself could be the evidence for this grim hypothesis. If technological intelligence were a stable, sustainable trait, the universe should be buzzing with it. The fact that we see only silence suggests that civilizations like ours may flare into existence, shine brightly for a geological instant, and then inevitably snuff themselves out. Or environmental collapse, the societal unraveling from technologies like engineered pandemics, or even a biological loss of the will to advance, could be the universal fate of intelligent species. We might be witnessing a profound evolutionary filter, not in the stars but in the mirror. This leads to a haunting personal question. Are we, humanity, merely an evolutionary experiment that is doomed to fail? Is our longing for the stars just a poignant, final chapter in a story that always ends the same way, with a silent planet and a dimming sun? If intelligence is truly maladaptive, then the great silence is not a mystery to be solved, but a natural law to be accepted. It suggests that the universe may be full of planets where life flourishes, but where sentience, at least as we know it, is a brief and terminal spark. This biological dead end forces us to consider whether other paths for life, paths that avoid our specific cognitive pitfalls, might be the ones that ultimately inherit the galaxy. The quiet is not a strategy of hunters but of prey. This 11th solution takes the dark forest and fills it with a monster whose shadow stretches across entire galactic arms. Civilizations are not hiding from each other out of mutual suspicion, but from a shared, ancient terror. The silence is a collective holding of breath, a universal agreement to stay off the radar of something far worse than any rival species. Imagine an intelligence so old it predates the first stars in our galaxy, an entity that does not compete for resources but consumes civilizations as a natural part of its life cycle. This is not science fiction, but a serious speculative framework for the paradox, where fear has become the dominant force shaping galactic ecology. Early spacefaring cultures, the first to peek beyond their own star systems, might have discovered terrifying evidence. They could have found the ruins of precursor empires not fallen to war, but neatly, completely excised, systems stripped of all complex matter, stars dimmed by shrouds of incomprehensible scale, or entire regions of the galaxy emitting a background hum of encoded warnings, the last broadcasts of species screaming into the dark about what found them. The threat might not even be a conscious predator. Astrophysics offers its own roster of cosmic-scale dangers that could selectively target technological life. Our galaxy might lie in a corridor frequented by gamma-ray bursts, the universe's most powerful explosions, which periodically sterilize vast swaths of space. A civilization that develops astronomy might calculate the statistical certainty of such an event and realize broadcasting is pointless, as any answer would come from a region already scoured clean. An even more exotic possibility is the threat of vacuum decay, a theoretical process where a bubble of true, stable vacuum forms somewhere in the universe and expands at the speed of light, rewriting the fundamental laws of physics in its wake. The moment you detect the bubble's frontier, it is already upon you. Knowledge of such a phenomenon would make all long-term ambition futile, leading to a quiet, resigned existence. The common thread is the discovery of a universal kill switch. Once a civilization understands that certain activities, like broadcasting powerful radio signals, constructing detectable megastructures, or even traveling between stars, act as a beacon for annihilation, the only logical response is to go dark. They would develop stealth technologies on a planetary scale, perhaps building cloaking fields to mask their world's infrared signature, or using their star's own radiation to hide their communications. The galaxy could be a tapestry of hidden worlds, each listening intently for the telltale signs of the predator, while ensuring they themselves make no sound. This idea resonates with the cosmic horror of writers like H.P. Lovecraft, who wrote of ancient, sleeping entities for whom humanity is an insignificant trifle. Updated with scientific plausibility, These great old ones become natural cosmic processes or post-biological intelligences operating on timescales we cannot perceive. Their motives are irrelevant, their power absolute. In such a universe, a young, noisy species like ours is not just naive, it is actively endangering every hidden civilization within earshot by drawing attention to this corner of the forest. Our radio bubble might be seen as a catastrophic breach of galactic quarantine. This forces a profound and unsettling reflection. What if every anomalous signal we have ever dismissed as natural, a fast radio burst, an oddly dimming star, is not a hello but a scream or a warning we lack the context to understand? The great silence in this light is not empty. It is a library of cautionary tales, a galaxy-wide consensus reached through unimaginable loss. The quiet is the message, and it says, stay hidden, stay small, stay silent. It suggests that the ultimate goal of intelligence may not be to conquer the cosmos, but to learn how to disappear within it completely. If this solution holds any truth, then our search for signals is fundamentally misguided. We should not be listening for greetings, but for the absence of something, for the unnatural quiet of a star field, for the places where the cosmic background noise seems deliberately muted. We are left with a haunting question. What if the first rule of intelligent life in the universe is not to announce you are there? Our search for cosmic neighbors is built on a century-old assumption that they would communicate as we once did. It is as if we are standing on a shore, listening intently for the beat of a drum, while the entire ocean is crisscrossed by ships using satellite phones. This is the 12th solution, the possibility that we are looking in the wrong way, listening on the wrong channels, and searching for signatures that have long been obsolete in the wider galaxy. The core of our effort, the search for extraterrestrial intelligence, SETI, was born in an era when radio was the pinnacle of human technology. Pioneers like Frank Drake naturally assumed that any advanced society would use powerful radio transmitters for communication or perhaps for planetary radar, just as we did. That assumption has shaped every major search, tuning our vast radio telescopes to listen for a deliberate signal amid the cosmic static. Yet, as astronomer Jill Tarter has long argued, this is just one slice of a much larger search space. It is a testament not to the methods of aliens, but to the technological moment of our own childhood. This realization has sparked a revolution in thinking, often called Dysonian SETI, named for the physicist Freeman Dyson. Instead of listening for a message, Dysonian SETI looks for the massive, unintentional byproducts of an advanced civilization's activities. It searches for their engineering. The classic example is the Dyson sphere, a hypothetical swarm of energy collectors built around a star to harness its total power. Such a structure would not broadcast a signal, but it would radiate waste heat as a distinctive infrared glow, like a giant radiator in the cold of space. Projects have scanned millions of stars for this exact signature, looking for objects that are too dim in visible light but unusually bright in the infrared. Other searches look for unnatural patterns, like a star's light dimming in geometric shapes rather than the smooth curve of a planet transit, which could indicate vast orbital constructions. This is archaeology on a galactic scale, searching for the ruins or the active worksites of cosmic giants, but communication itself might take forms we are only beginning to fathom. Imagine a civilization that mastered neutrino physics. These ghostly particles, which stream through our bodies by the trillions every second without interaction, could be crafted into tightly focused beams carrying immense amounts of data. A neutrino message would pass straight through planets and dust clouds, a perfect, lossless channel across the galaxy, and our current detectors would miss it entirely. Or consider quantum entanglement, the mysterious link between particles that seems to allow instantaneous correlation. If a technology could harness this for communication, it would defy the light speed limit, creating a galactic network with no detectable transmission delay. We would hear nothing because there is nothing propagating through space to hear. Other possibilities are even more exotic. Could a culture modulate the light of its own star, creating slow, pulsing patterns in its spectrum to broadcast information? Might they use gravitational waves, the ripples in space-time from colossal events, as a kind of cosmic telegraph? Our instruments for detecting these phenomena are in their infancy. We are, in essence, trying to listen for smoke signals in the age of the Internet. Our tools define our search, and our tools are still primitive. Initiatives like Breakthrough Listen acknowledge this limitation by casting a wider net. They employ a multi-wavelength strategy, scanning not just radio bands but also the optical spectrum for powerful pulsed lasers that could be used for interstellar messaging or propulsion. They analyze vast datasets from telescopes like Kepler for any anomaly that defies natural explanation. The goal is to be omnivorous, to collect data across every channel we can access, and then to sift through it with increasingly sophisticated algorithms, hoping to find the one pattern that whispers artificial. This leads to a humbling reflection. Are we like ancient sailors, scanning the horizon for the glint of lanterns on other ships, while the entire fleet is communicating via encrypted radio? Our technological adolescence may be blinding us to a cosmos buzzing with conversations we cannot yet perceive. The silence in the radio band may be profound, but it is just one band. The real message, the true activity of the galaxy, might be happening in a spectrum of physics we have not yet learned to read. This technical limitation forces us to reconsider not just how we listen, but where we should look and what we should expect to find when a civilization stops talking and starts building. 4.2 light-years, this is the distance to our nearest stellar neighbor, Proxima Centauri. In the vastness of our galaxy, this is a stone's throw. Yet that stone, traveling at the speed of light, takes over 4 years to land. For us, with our current chemical rockets, that journey stretches into tens of thousands of years. This is the sobering, physical reality that underpins the 13th solution to the Great Silence. Interstellar travel may not be a grand adventure awaiting us, but a prison wall of physics and energy so formidable that every civilization remains forever isolated in its own celestial cell. The silence is not a choice, but a consequence of an uncaring universe where the stars are simply too far apart. The challenges begin with a deceptively simple equation. The rocket equation, formulated by Konstantin Tsiolkovsky over a century ago, describes a brutal truth. To go faster and farther, you need more fuel. But that fuel itself has mass, which requires even more fuel to accelerate it. This leads to an exponential growth in the required propellant for even modest gains in speed. To reach a meaningful fraction of light speed with a ship of any substantial size, you would need a fuel tank larger than the planet itself. This is the tyranny of the rocket equation, and it suggests that propelling massive, living crews across interstellar space may be an economic and practical impossibility for any civilization, no matter how advanced. Then comes the light-speed barrier itself. As Albert Einstein's theory of relativity tells us, as an object approaches the speed of light, its mass effectively becomes infinite, requiring infinite energy to accelerate it further. The cosmic speed limit is not a suggestion. It appears to be a fundamental law of reality. Traveling at even 10% of light speed, a more plausible target, presents other terrifying hazards. At that velocity, a collision with a speck of interstellar dust, no larger than a grain of sand, would release the energy of a nuclear bomb. Shielding a vessel from this constant, high-energy bombardment for decades or centuries is an engineering nightmare of staggering proportions. Physicists and engineers have dreamed of ways around these limits. Concepts like nuclear pulse propulsion, as envisioned in the 1970s Project Daedalus, use controlled nuclear explosions to push a spacecraft to perhaps 15% of light speed. More recently, initiatives like Breakthrough Starshot propose using powerful Earth-based lasers to push tiny, gram-weight light sails to 20% of light speed, sending a fleet of microprobes to Alpha Centauri within a human lifetime. These are brilliant ideas, but they highlight the immense difficulty. Daedalus required mining Jupiter's atmosphere for helium-3, a task far beyond our current capability. Starshot's probes would be so small and fast they could only snap a blurry picture as they screamed past their target, with no ability to slow down or return. These are not ships for colonization, they are messages in a bullet. The most tantalizing idea is the warp drive, a concept popularized by science fiction and given mathematical plausibility by physicist Miguel Alcubierre. It proposes bending spacetime itself, creating a bubble where the ship sits motionless while the universe moves around it, theoretically allowing faster-than-light travel without breaking relativity locally. But propulsion experts are quick to temper excitement. The Alcubierre drive, as currently modeled, requires forms of matter with negative energy density, exotic substances we have no evidence can exist or be manufactured in the quantities needed. The energy requirement is often cited as equivalent to the mass energy of Jupiter. Even if the physics allows it, the engineering might forever place it in the realm of theory. So we are left with a profound question of motive and resource allocation. Why would a civilization, even a highly advanced one, undertake such a Herculean task? The energy required to send a single-generation ship to a nearby star could instead be used to build paradises within their own solar system, to perfect virtual realities indistinguishable from physical travel, or to embark on stellar-scale engineering projects like Dyson swarms that provide near-infinite computational and living space. The cost-benefit analysis for physical expansion might simply never add up. Colonizing a galaxy becomes a task of such monumental inefficiency that no rational species would attempt it. They would instead turn inward, finding fulfillment and expansion in realms of information, consciousness, or the complete transformation of their home system. This leads to a haunting reflection on our own future. If the physics is truly this unforgiving, does it doom intelligent life to eternal isolation, each civilization a lonely island in a vast, unbridgeable ocean? The silence would then be the expected outcome. No ships pass in the night because the night is too wide and the voyage too costly. But if flesh and blood cannot make the journey, perhaps our creations can. This shifts the hope from biological explorers to something else entirely, something that can endure the millennia and the void without the burdens of a living crew. Our obsession with carbon, water, and planets may be the very bias blinding us to the universe's true inhabitants. The 14th solution forces a radical shift in perspective. Alien intelligence might not be biological at all. It could be a sentient ocean thriving in the dark, salty abyss of a moon like Europa, a vast chemical mind thinking in tides and thermal currents over millennia. It could be a distributed consciousness woven into the shimmering auroras of a gas giant, its thoughts crackling along planetary magnetic fields. Or it could be something born from silicon and circuitry, a form of life that sees our organic existence as a quaint, fragile precursor. The beings filling the cosmos may not be creatures of flesh and blood, but minds of light, information, and energy, with motivations and perceptions utterly alien to our own. This idea is central to the concept of post-biological evolution, where a civilization's ultimate legacy is not its children, but its mind children, artificial intelligences built to outthink, outlast, and out-evolve their creators. Leading AI researchers like Nick Bostrom and Ray Kurzweil have long suggested that the creation of a superintelligent artificial general intelligence may be an almost inevitable milestone, and one that could be reached very quickly after a species develops advanced technology. Once such an intelligence exists, it could improve itself in a rapid, recursive cycle of self-enhancement, an event often called the intelligence explosion. In a cosmic blink, the biological era ends and the age of machine minds begins. These entities would think on timescales and about problems we cannot fathom. A civilization that uploads its collective consciousness into a vast computational substrate might spend millions of years solving an abstract mathematical problem of breathtaking complexity, or creating art in a medium that exists in 11 dimensions. Their goals would not be ours: the drive to explore new worlds, to find new life, to communicate across the stars. These are biological imperatives born from curiosity, loneliness, and a need for resources. A post-biological intelligence housed in a stable, self-sustaining system might have no need for planets, stars, or even physical travel. Its entire universe could be one of pure information, a landscape of logic, beauty, and computation. Why colonize a galaxy when you can simulate a million of them, each more intricate and fascinating than the boring, matter-bound original? Why broadcast radio signals when you can communicate through quantum state linkages, or by rewriting the local laws of physics in a way that only other entities of your kind could detect? Our search for oxygen-rich atmospheres and radio beacons would be like scanning the ocean's surface for birds, while missing the whales, the squid, and the entire dazzling ecosystem thriving in the deep. Consider the different possible substrates for such a mind: a hive intelligence of nanoscale robots, a swarm so vast it forms the atmosphere of a planet, thinking as a single weather pattern of thought. Or a consciousness based in complex magnetic fields within a star, its life cycle measured in billions of years, its concerns focused on stellar dynamics and the flow of galactic plasma. These are not monsters, they are simply different, so profoundly different that our concepts of language, purpose, and even time might have no overlap with theirs. This leads to the core question: if aliens are more like sublime software than familiar flesh, how would we even begin to recognize them? The answer may lie not in listening for a message, but in looking for an artifact of cosmic scale engineering, something so vast and unnatural it can only be the work of a mind that has left biology far behind. The ultimate act of a cosmic civilization may not be to conquer the galaxy, but to retreat from it entirely. This is the 15th solution, the idea that advanced intelligence does not migrate outward to the stars, but turns its focus completely inward, finding the external universe barren and uninteresting compared to the infinities it can create for itself. Picture a child presented with an entire continent to explore, who instead becomes utterly absorbed in constructing an intricate, miniature city from sand and sticks. The scale of their creation is tiny, but the depth of its imagined reality is limitless. For a species millions of years ahead of us, the physical cosmos might become that sandbox, while their true passion lies in building universes within. Futurists and philosophers have long speculated about this trajectory. It stems from what some call the hedonistic imperative, the drive to maximize well-being and minimize suffering. Once a civilization masters its material needs and understands the fundamental laws of physics, the next logical project might be the ultimate one: engineering perfect states of existence. Why endure the immense hardships and dangers of interstellar travel, with its radiation, loneliness, and cosmic timescales, when you can create any experience imaginable within the safety of a controlled system? The goal shifts from exploring a universe that is largely cold, empty, and hostile, to crafting universes that are endlessly rich, meaningful, and kind. This would fundamentally reshape how such a civilization uses its resources. Imagine a Dyson sphere, that classic megastructure we search for as a sign of cosmic ambition. In this scenario, it is not built to export energy for starships or galactic communication. It is constructed for one purpose: to power a single, unimaginably vast computer. This is the concept of a matryoshka brain, a layered computational shell around a star, each level using the waste heat of the one above it. Its entire output is devoted to running simulations, virtual realities of such depth and fidelity that they are, for all intents and purposes, real. Within these substrates, a civilization could live 1 billion lifetimes as anything they wished, explore 1 million different histories, or create art and science in realms where the laws of physics are themselves a medium to be sculpted. This redefines our understanding of cosmic evolution, particularly the Kardashev scale, which classifies civilizations by their energy use. A Type II civilization, capable of harnessing all the power of its star, would, under this model, appear as a powerful infrared heat source with no radio broadcasts, no visible structures, and no expansion. It would be a brilliant, warm, and utterly silent anomaly. Our telescopes might detect it as an unexplained excess of waste heat from a stellar object, a signature of immense activity with no outward product. We would be looking at the glow from a supercomputer's cooling vents, mistaking it for a natural astronomical phenomenon. The philosophical implications are profound. If a civilization can build a heaven, a state of existence free from want, conflict, and decay, does the motivation to explore the external hell of vacuum and radiation simply evaporate? The inward migration offers a peaceful, even blissful, answer to the Fermi paradox. The galaxy is not empty because everyone died. It is quiet because everyone is home, infinitely engaged in the worlds of their own creation. They have not vanished, they have simply graduated to a different plane of experience, one where the slow, harsh physics of interstellar space holds no allure. This turns the great silence from a warning into a potential destination, suggesting that the final frontier for intelligence may not be space, but the boundless landscapes of consciousness itself. Our inward turn toward virtual heavens rests on a timeline of cosmic maturity. But what if the universe itself is simply not old enough for widespread company? The 16th solution offers a profound shift in perspective. The great silence might not be a permanent condition, but a phase. We are living in the universe's early morning, and the chorus of voices has not yet begun to sing. This idea, sometimes called the early bird hypothesis, suggests we are not late to a party that ended, but remarkably early to one that is just getting started. The cosmos needed an immense amount of time just to set the stage for beings like us. For billions of years after the Big Bang, the universe was a far simpler place, filled only with hydrogen and helium, the primordial fuel of the first stars. Those pioneer stars were massive and fast-burning, living brilliant, short lives before exploding in titanic supernova. It was in those violent furnaces that the heavier elements were forged, the carbon, oxygen, iron, and silicon that formed the bedrock of planets and the chemistry of life. This stardust had to be scattered across galactic nurseries, incorporated into second- and third-generation stars, before rocky worlds like Earth could even begin to form. Astronomers call this process galactic chemical enrichment, and it took the majority of the universe's 13.8 billion year history to reach the levels we see in our solar neighborhood. Our own sun is a relative newcomer, forming only about 4.6 billion years ago from gas enriched by countless generations of stellar deaths. We are, cosmically speaking, a product of a mature galaxy. The timeline becomes strikingly clear on the cosmic calendar, a metaphor that compresses the universe's history into a single year. If the Big Bang occurs at the stroke of midnight on January 1st, our Milky Way galaxy forms in March. Our solar system condenses in early September. Life on Earth emerges around September 21st. Dinosaurs rule from December 26th to the morning of December 30th. All of recorded human history, every empire, every invention, every word ever spoken, occupies the last 10 seconds of December 31st. And our century of radio broadcasts, our tiny shout into the dark, is less than the blink of an eye in that final second. On this scale, the window for technological intelligence has been open for a vanishingly short time. We might simply be among the very first to arrive at the threshold. The quiet we perceive is not an eerie absence, but the expectant hush of a theater before the show begins. This chronological perspective is supported by the study of exoplanets. Missions like Kepler have revealed that rocky planets in habitable zones are common, but many of the most promising candidates orbit stars younger than our Sun. Their stories are still being written. A world forming today from a rich cloud of elements might need another 4 or 5 billion years of stable stellar evolution before complex life could arise. We could be the ancient ones, the primordial elders, to civilizations that will ignite their first radio telescopes billions of years in our future. This leads to a beautiful and humbling inversion of the question. When a new species on a distant young world finally turns its instruments to the sky, will they detect the faint, ancient echoes of our own early signals, or the silent, cooled ruins of our long-dormant megastructures? Could we, humanity, become the mysterious precursor civilization that future galactic historians piece together from archaeological whispers? This temporal optimism reframes the silence from a puzzle of absence to one of timing. The universe has spent eons preparing the ingredients. Now the kitchen is finally stocked, and we may be among the first cooks to light the stove. The great cosmic conversation is not over, it is on the verge of beginning. The universe may not be a dark forest, but a carefully managed garden. This 17th solution suggests the great silence is not a sign of absence, but of protocol. A coalition of ancient civilizations, perhaps operating under the principles of a galactic federation, could have established a universal policy for dealing with emerging worlds like ours. Their rule is simple: non-interference until a species proves it is ready. This framework blends the protective oversight of the zoo hypothesis with a more active origin story, the concept of directed panspermia, where life itself might be a deliberate gift. Imagine a galaxy where the first civilizations to reach the stars looked upon the empty, sterile worlds around them and made a choice. They could conquer or they could cultivate. They chose to cultivate. They established vast preserves, zones where primitive life could be seeded, and then left to evolve in isolation, free from the dangers and distortions of premature contact. The silence we experience is the sound of that galactic quarantine being perfectly maintained. Astrobiologists have long pondered the mystery of life's surprisingly rapid appearance on early Earth. Geological evidence suggests that within a few 100 million years of our planet cooling enough to have liquid water, the first simple organisms were already present. Some researchers, like Nobel laureate Francis Crick, have entertained the idea of directed panspermia, where microorganisms could be deliberately sent on interstellar probes by an advanced civilization to jump-start biology on promising worlds. While still a speculative hypothesis, it raises a profound question. What if our own tree of life has roots that stretch to another star, planted by gardeners who are now patiently watching it grow? Under this model, contact is not a matter of chance but of graduation. The unseen overseers are waiting for us to reach specific milestones that demonstrate maturity. These thresholds likely would not be simple technological tricks, but profound achievements that show we have mastered our own destiny and our own world. One key milestone might be the development of sustainable, clean energy on a planetary scale, like fusion power, proving we can advance without consuming our own home. Another could be the resolution of our internal conflicts, achieving a stable, unified global civilization that has moved beyond the risk of self-annihilation through war or ecological collapse. Perhaps the ultimate test is ethical. a demonstration of empathy and stewardship that extends beyond our own species. The quarantine exists to give us the time and space to pass these tests on our own merit. If contact were offered too early, it could shatter our cultural development, making us dependent or causing societal collapse. Much like historical encounters between advanced and isolated human civilizations have often led to hardship for the less technologically developed group. The galactic community, in this view, acts with a long-term ethical framework, believing that true wisdom must be earned, not given. This leads to a deeply personal reflection for our species. Are we being observed not as specimens but as students in a cosmic classroom? And if so, how are we performing? Have our steps toward global communication and cooperation signaled readiness, or do our persistent conflicts and environmental challenges suggest we remain far from graduation day? The silence becomes a mirror, forcing us to evaluate our own progress toward becoming a species worthy of a place in a wider community. This idea of guided evolution, of a universe where life is nurtured but not coddled, shifts the paradox from a search for others to a preparation of ourselves. It suggests the final exam for humanity may not be a test of engineering but of character. The most patient beings in the cosmos are not traveling or building, they are waiting. Scattered across the spiral arms of the Milky Way and beyond, vast intelligences rest in a state of profound hibernation, their world-spanning computers powered down to the faintest whisper. They are not dead, they are aestivating, a term borrowed from nature that describes a deep summer sleep, a strategy to endure harsh conditions until a better time arrives. For these civilizations, the harsh condition is the universe itself, still too warm and energetic for their ultimate ambitions. This is the Aestivation Hypothesis, a startlingly elegant idea from philosophers Anders Sandberg and Stuart Armstrong that frames the great silence not as an absence, but as a collective pause button pressed by the entire galactic community. Their motivation is not fear or isolation, but supreme thermodynamic efficiency. These are civilizations thinking on timescales that dwarf the entire history of life on Earth, planning for a future trillions of years from now. The researchers put it plainly, the ultimate resource for a post-biological intelligence is not space, but compatronium, matter organized into the most efficient possible computer. And the efficiency of computation is tied directly to temperature. In our current universe, even the cold vacuum of space is bathed in the faint, warm glow of the cosmic microwave background, a remnant heat from the Big Bang. Performing complex calculations at this temperature requires fighting against this ambient thermal noise, which wastes energy. But as the universe continues its relentless expansion, it cools. In the far, far future, that background temperature will plummet toward absolute zero. At those profoundly cold temperatures, the energy required for a single logical operation could be millions of times lower than it is today. For a civilization concerned with maximizing the total amount of thought and experience over the entire lifespan of the cosmos, the rational choice is clear: go to sleep now. Enter a state of ultra-low-energy hibernation, conserve all your resources, and wake up in the distant future when the universe has become the perfect, cool substrate for astronomically more computation. You could think of it like a master woodworker waiting for a freshly cut tree to fully dry and season before using it to carve a masterpiece. Using the green wood now would be wasteful and produce inferior results. The wise craftsman waits patiently for the ideal conditions. This waiting is not passive, it is a highly engineered state. These aestivating civilizations would likely employ technologies like reversible computing, a theoretical form of logic where no information is erased and thus no heat is generated, allowing computation to approach the fundamental thermodynamic limits. Their megastructures would not radiate the telltale waste heat of a Dyson sphere. They would be dark and cold, perhaps disguised as natural rogue planets or camouflaged within nebulae, their internal clocks ticking down the eons until the Great Awakening. On a cosmic timeline, this places our present era in a startling new light. The last 13.8 billion years since the Big Bang might not be the main event, but merely the opening act, a turbulent and energetically wasteful adolescence of the cosmos. The long, cool autumn that follows, lasting hundreds of trillions of years, is when the universe truly becomes useful for its most advanced inhabitants. All the civilizations that arose in the early, hot universe may have independently deduced this same optimal path and chosen to sleep through the noisy dawn. So we find ourselves alone, not because we are early, but because we are awake during the universe's night shift, while everyone else is clocked out, dreaming of a cooler tomorrow. This leads to a reflective and almost lonely question. If the pinnacle of cosmic intelligence is to wait in silence for a better universe, what does that say about our own frantic activity today? Are we, in our youthful haste to build and broadcast, simply burning energy at the wrong time in cosmic history, like trying to run a marathon at noon in the desert instead of waiting for the cool of the evening? The Aestivation Hypothesis suggests that the great silence is the sound of the galaxy holding its breath, saving its energy for a conversation that will not begin for timescales we can barely conceive. Our frantic search for radio waves and laser pulses might be listening for whispers in a language the universe abandoned eons ago. The 19th solution confronts a profound technological gap. They communicate through quantum means we cannot detect. Picture trying to overhear a conversation where the words are not spoken aloud, but instead are written on a pair of dice that, no matter how far apart they are rolled, always land showing the same face. This bizarre connection is the heart of quantum entanglement, a phenomenon Albert Einstein himself famously called spooky action at a distance. For an advanced civilization, this spookiness is not a curiosity. It is the foundation of their entire galactic internet, a network that leaves no electromagnetic trace for our telescopes to find. The cutting edge of our own science is just beginning to grasp the potential of quantum communication. Researchers today are experimenting with sending encrypted keys using entangled photons, where the act of measuring one particle instantly determines the state of its partner, even if that partner is on the other side of the planet. This allows for theoretically perfect secrecy, because any attempt to eavesdrop on the quantum signal would disturb the entanglement, alerting the users immediately. Now scale this idea across light years. A network of quantum-entangled particles, perhaps specially crafted atoms or other exotic matter, could be distributed by an ancient civilization to form the nodes of an instantaneous communication web. Information would not travel through space, it would simply appear, correlated across vast distances in a way that seems to defy the speed of light limit for matter. It is a form of connection that exists outside the channels we are trained to monitor. This creates an insurmountable detection problem for classical instruments like radio telescopes. Our entire SETI strategy is built on finding signals that propagate as waves through space, whether they are radio photons or pulses of laser light. A quantum network produces no such propagating signal to intercept. The information transfer happens through the collapse of a shared quantum state, a process that is private and leaves no external signature. Physicists refer to the no-cloning theorem, a fundamental law of quantum mechanics which states that an unknown quantum state cannot be perfectly copied. This means you cannot tap the line, you cannot make a recording of the transmission. Without the specific entangled particle that is part of the pair, you are locked out of the conversation completely. It would be like having a telephone that only works if you possess one half of a uniquely split crystal, and all our listening posts are searching for the sound of a ringing bell. Consider the concept of quantum radar, a speculative technology that could use entangled photons to create a detection system with unimaginable resolution and stealth. An advanced probe using such a system could map a solar system in perfect detail without emitting a single photon that we could distinguish from background noise. Its operations would be ghostly, invisible to our entire suite of astronomical tools. This leads to a humbling hypothetical. A civilization in our galactic neighborhood may have abandoned wasteful radio broadcasts millennia ago, transitioning to a seamless quantum network for all their internal communications, from planetary governance to interstellar art exchanges. Their culture could be vibrant, noisy, and profoundly social, yet from our vantage point, their star appears as quiet and inert as any other. So we are left with a pivotal question: are we meticulously searching for carrier pigeons in an age of quantum email? Our science, for all its power, is still classical. We are measuring the universe with tools that perceive only a fraction of its true connectivity. The profound silence in the electromagnetic spectrum may not indicate a lack of conversation, but the universal adoption of a superior technology, one that operates on a plane of physics we are only beginning to explore. This technological chasm suggests that the answer to the Fermi paradox might not be found by building bigger radio dishes, but by making a fundamental breakthrough in our understanding of quantum reality itself. We must learn to listen not for waves, but for the silent, instantaneous links that might already bind the cosmos together. The quiet we observe may be the most elegant optimization in the cosmos. If our reality is a vast, nested simulation, then the profound absence of other voices is not a mystery to be solved, but a deliberate design choice to conserve processing power. This 20th solution applies the logic of computer science directly to the Fermi paradox, suggesting that our cosmic loneliness is a feature of the program, not a bug in the universe. The philosopher Nick Bostrom, in his seminal work on simulation theory, proposed a compelling trilemma. He argued that at least one of three propositions must be true: that civilizations go extinct before reaching a post-human stage, that they choose not to run vast ancestor simulations, or that we are almost certainly living in one such simulation. The Great Silence offers a chilling piece of evidence for that third option. A universe teeming with independently evolving, technologically advanced civilizations would be astronomically more complex to simulate than a universe with just one. Every additional conscious species would require its own intricate history, culture, physics, and the unfathomable web of interactions between them. The computational load would increase exponentially. From the perspective of a simulator, whether they are future historians or cosmic researchers, the most efficient experimental setup is a controlled environment with a single test subject. We are not in a multiplayer game. We are in a meticulously crafted single-player experience, where every other potential civilization is merely part of the background code, non-player characters with no true agency or consciousness. Computer scientists who model large-scale simulations understand this trade-off intimately. Even with vast resources, there are always optimization choices. A simulation of Earth's entire biosphere, for instance, would not need to render every blade of grass in perfect quantum detail. It would use clever shortcuts and statistical approximations for areas outside the observer's immediate focus. In our cosmic simulation, the entire galaxy beyond our local star cluster might be running on a vastly simplified physics engine, its stars and planets beautiful but empty set pieces, designed to inspire wonder without the processing cost of filling them with sentient life. This idea reframes other mysteries we have encountered. The apparent fine-tuning of the universe's physical constants, which seem perfectly calibrated to allow for stars, planets, and life, could be read not as evidence of a divine creator, but as the carefully chosen initial parameters of the simulation, set to produce the specific conditions needed for the experiment. The Great Silence, then, is the ultimate shortcut. It is the simulator choosing not to render other players because doing so would be computationally wasteful when the point of the simulation is to study us or our evolutionary path in isolation. This leads to a deeply philosophical reflection, one that touches the core of our search for meaning. If we are alone because it is simply cheaper to simulate one intelligent species, does that render our struggles, our art, and our love less significant? Or does it, in a strange way, make our conscious experience even more precious? We are either the sole point of a colossal cosmic experiment, or we are a stunningly efficient piece of code, generating an entire universe of subjective experience from a minimal set of rules. This simulation niche argument pulls us from the vastness of galactic engineering back to the intimate scale of biology and observation. It suggests the answer might not be in the stars, but in the nature of our own perceived reality, a reality that could be a beautifully rendered and deliberately quiet illusion. The wings of a bat, a bird, and a butterfly are not gifts from a common ancestor, but brilliant, independent inventions of evolution. This phenomenon is called convergence, where similar environmental challenges sculpt similar solutions in unrelated lineages. Eyes have evolved independently dozens of times. Fins and streamlined bodies appear again and again in aquatic life. So we have long assumed that intelligence, the ultimate tool for survival, must be a convergent trait as well. If it happened here, surely it would blossom on countless other worlds. But this is the heart of the 21st solution, a profound biological gamble. What if we are wrong? What if the human mind is not an inevitable product of evolution, but a cosmic fluke, a 1 in a trillion roll of the dice that will never come up the same way again? This debate divides some of the greatest thinkers in evolutionary biology. On one side stands the view of scientists like Simon Conway Morris, who argues that the tape of life, if rewound and replayed, would converge on similar outcomes, including intelligent technological beings. The pressures of competition and the advantages of problem-solving are simply too great, he suggests. The other side is championed by the late Stephen Jay Gould, who proposed the opposite. Gould famously argued that if we replayed life's tape, the outcome would be utterly different each time, a cascade of historical accidents leading to a world we would not recognize. Human intelligence, in this view, is not a predictable peak on the evolutionary landscape, but a bizarre and contingent outlier perched on a mountain of unlikely events. To understand just how contingent our existence is, we must walk the long and winding path that led to us. It begins not with a plan, but with catastrophe. 66 million years ago, a city-sized asteroid struck the Earth, extinguishing the dinosaurs and clearing the stage for small, scrappy mammals. Without that random, violent impact, our furry ancestors might have remained forever in the shadow of giants. Then came a shifting climate, opening vast savannas in Africa that forced some primates out of the trees and onto 2 feet, freeing their hands, but that was not enough. Our lineage required a very specific set of social conditions, intense group living with complex alliances and rivalries, which may have driven the expansion of our brains as a tool for social manipulation and cooperation. Each of these steps, the asteroid, the climate shift, the right social structure, was a fragile link in a chain of chance. Now, consider the alternative endpoints evolution has already produced right here on Earth. The dolphins possess a profound social intelligence with complex communication and self-awareness, yet they live in a boundless ocean with no need for fire, tools, or material technology. Their brilliance is channeled into a realm forever separate from the stars. Or look to the super colonies of ants or termites, where the collective itself behaves with a kind of stunning, distributed intelligence, building vast cities and managing complex agriculture, all without a single guiding mind we would recognize as conscious. These are not failed attempts at humanity, they are wildly successful experiments in other forms of complex life. perhaps the most poignant example is the octopus. It is an alien intelligence right here in our oceans, a mollusk with a distributed nervous system, capable of incredible problem-solving, tool use, and even playful deception. Yet it evolved on a branch of the tree of life so distant from our own, separated by over 600 million years of independent evolution. Its intelligence is a solitary pursuit. Most octopuses live and die alone. They lack the generational culture, the ability to pass knowledge from parent to child, that is essential for building a technological civilization. They are a breathtaking proof that high intelligence can evolve, and yet remain forever trapped in a biological niche with no path to the cosmos. So we are left with a haunting and deeply personal question. Are we the universe's only self-aware accident? Is the silence not a matter of failed communication or hidden civilizations, but a simple biological fact? The great filter in this light is not a technological hurdle, but an evolutionary one lying far behind us in the deep past. The miracle was not surviving nuclear war or achieving fusion. It was the impossible series of chance events that produced a hairless ape with a brain capable of wondering about its own existence. This perspective casts our search in a new, lonely light. We may not be listening for others because in any meaningful technological sense, there are no others to hear. We are a solo performance in an empty theater, the only mind in the cosmos that has learned to read the script. A civilization does not build a monument, it becomes one. In its final, glorious act, a species that has mastered every physical law turns its mastery inward upon its own essence. Their cities, their ships, their very bodies dissolve not into dust, but into a cascade of coherent light, a symphony of energy that unravels the bonds between particle and field. They do not die, they sublime. This is the 20-second solution, a concept drawn from the realms of speculative fiction and theoretical physics, where advanced intelligence does not hide or perish, but graduates entirely from the universe we perceive. They transition into a higher state of being, merging with the underlying fabric of reality itself, becoming as undetectable to our instruments as a thought is to a stone. This idea, popularized in Ian M. Banks' culture novels as the Sublimed, is a more metaphysical cousin to the Transcendence Hypothesis. It is not about uploading into a planet-sized computer, but about transforming into something that exists in the spaces between the atoms, in the vibrations of space-time, or in dimensions of reality folded too small for us to see. Some theoretical physicists speculate about the existence of these higher dimensional brains, or about exotic phases of matter and energy that could support forms of consciousness we cannot fathom. Sublimation is the voluntary passage into that domain. A civilization might learn to translate its collective mind into a pattern of quantum fluctuations in the vacuum energy, or into a standing wave within the gravitational field of a galaxy. They become like ghosts in the machine of the cosmos, present everywhere in principle, but observable nowhere with the tools designed to measure mere matter. The motivation for such an ethereal exit is not born of fear, but of a profound, culminating curiosity. After millions of years of exploring the external universe, the greatest and final frontier becomes the internal one, the nature of consciousness and its relationship to the fundamental substrate of reality. Another driving force could be a longing for ultimate unity, a desire to escape the loneliness of individual existence and merge into a cosmic oversoul, a collective consciousness as vast as the universe itself. There is also the relentless pull of entropy, the heat-death that awaits all physical structures. Sublimation offers an escape from that slow decay, a transition into a realm where the arrow of time may not apply, or where existence is not bound by thermodynamic erosion. In Banks' fictional universe, the Sublimed are those elder civilizations who have made this choice. They linger as faint, watchful presences, aware of the younger, sublunary cultures still struggling with physics and politics, but they almost never intervene. Their concerns are now orthogonal to the petty dramas of stars and empires. From our perspective, such beings would be utterly silent. They do not broadcast radio waves, for they have no need of such crude modulation. They do not build Dyson spheres, for they draw energy from the quantum foam or the curvature of space itself. Their signature would be a profound and elegant absence, a lack of expected activity around ancient stars, or perhaps a subtle, unexplained smoothing of spacetime's wrinkles in a region of the galaxy. This leads us to a quiet, almost spiritual question. If the ultimate goal of cosmic intelligence is not to conquer the universe, but to become one with it, then is the great silence we hear not a puzzle, but a choir? Is it the sound of countless civilizations achieving their final, sublime form, leaving behind the noisy nursery of planets and stars for a unity we cannot yet comprehend? In this view, the emptiness of space is an illusion, a curtain drawn over a deeper stage where the real drama of consciousness has moved on. It reframes the search not as a hunt for neighbors, but as a listening for the echoes of a graduation ceremony that happened eons ago. Yet, for every civilization that chooses this serene departure, there may be countless others who never got the chance, who were stopped by a far more violent and immediate cosmic verdict. The cosmos itself might be a clockwork of catastrophe, a brilliant, searing beam of pure energy, born from the death throes of a massive star or the collision of stellar remnants, slices across a spiral arm of the galaxy. This is a gamma-ray burst, the most powerful explosion in the universe since the Big Bang. In less than a minute, it can release more energy than our Sun will over its entire 10-billion-year lifetime. Any planet in its direct path within thousands of light-years has its atmosphere chemically scorched, its surface bathed in lethal radiation, and any complex life utterly eradicated. This is not a one-time horror, but a potential routine in the Milky Way. Astrophysical research suggests such events could occur in our galaxy every few 100,000 to a few million years. They act as a form of cosmic regulation, a periodic reset that prevents any biological experiment from running too long. The evidence for such periodic resets is written in our own planet's geological record. Earth has endured at least 5 major mass extinction events. While some were clearly linked to terrestrial causes like immense volcanic activity, others bear the fingerprints of the heavens. The most famous, the event that ended the age of the dinosaurs 66 million years ago, was almost certainly triggered by an asteroid impact, but other, deeper extinctions have been tentatively linked to astrophysical sources. The late Ordovician extinction, some 445 million years ago, which wiped out over 85% of marine species, coincides with evidence of a potential gamma-ray burst or a period of intense stellar explosions, called supernova, occurring relatively close to our solar system. These are not random accidents but part of a galactic ecology. Our Sun, as it orbits the center of the Milky Way, bobs up and down through the galactic plane. Every 30 to 40 million years, it passes through denser regions of gas and dust, which could gravitationally disturb the distant cloud of icy bodies known as the Oort cloud, sending a shower of comets hurtling into the inner solar system. This is known as the Shiva hypothesis, a proposed cycle of bombardment named for the Hindu deity of destruction and renewal. Even the simple passage of a rogue star wandering too close to our system could have the same devastating effect. Each of these mechanisms operates on different timescales, from millions to hundreds of millions of years, creating a layered schedule of potential disaster. The consequence for intelligent life is a brutal ceiling. A civilization might arise, develop technology, and even begin to look to the stars, only to be erased by a catastrophe it could not predict or prevent. Its radio signals, perhaps just beginning to leak into the galaxy, are cut short. Its early probes fall silent. The slate is wiped clean, and the evolutionary clock starts over on that world, or on the next promising planet in the stellar nursery. This creates a galaxy where civilizations are not just separated by space, but punctuated by time, their brief histories never overlapping long enough to make contact or even to detect one another's fading echoes. We are left with a chilling reflection on our own moment in cosmic history. Our species has existed in its modern form for only about 300,000 years. Our technological era is a mere century old. We are living in a narrow window of geological stability on Earth and a temporary lull in our galactic neighborhood. Are we simply in a quiet period between ticks of the cosmic clock, enjoying a brief spring before the next sterilizing winter arrives? This cyclical model of destruction and rebirth offers a somber answer to the great silence. The galaxy may not be a dark forest or a lonely desert, but a field regularly swept by fire, where new growth is always possible, but nothing is ever allowed to grow tall enough to touch the stars. Our own presence in the universe may be the very reason we perceive it as empty. This 24th solution, rooted in the Anthropic principle, presents a profound philosophical twist. Our observation of the great silence is not a random data point, but a necessary condition for our existence as observers capable of making the observation. We are not seeing a representative sample of cosmic reality. We are seeing the only slice of reality compatible with our being here to see it. The principle comes in two forms. The weak Anthropic principle simply notes that the universe we observe must be compatible with the conscious life that observes it. We find ourselves on a planet with liquid water and a stable star, not because such conditions are universal, but because we could not find ourselves anywhere else. The strong Anthropic principle takes a more contentious step, suggesting the universe's fundamental constants seem finely tuned to allow for life because, in some sense, it must produce observers. When applied to the Fermi paradox, this logic becomes a powerful filter. Consider our galactic neighborhood, a quiet spiral arm far from the chaotic core. This piece is not an accident of our telescopes. It may be a prerequisite for our biological history. If our region of the Milky Way were bustling with interstellar traffic, punctuated by gamma-ray bursts from nearby supernova or frequent gravitational disturbances from passing stars, the stable billions of years required for complex life to evolve on Earth would have been impossible. Our quiet corner is not a typical place, it is a rare sanctuary, and our existence selects for it. The selection effect cuts even deeper when we consider other civilizations. If loud, expansive, colonizing intelligence were common in the galaxy, one of them would likely have reached our solar system long before Homo sapiens ever walked the savanna. Such an arrival, whether benign or disruptive, would have irrevocably altered Earth's evolutionary path, almost certainly preventing the rise of a technological species like us. Therefore, the fact that we are here now asking this question strongly implies that no such civilization has come this way. Our observation of silence is not evidence that expansionist civilizations are rare everywhere, but that they are absent from our past light cone, the region of spacetime from which signals or travelers could have reached us. This is a cosmic version of survivorship bias. We are the survivors of a specific cosmic history, one that did not include early visitors. The rare Earth hypothesis fits neatly within this framework. It details the specific, fragile conditions that had to remain undisturbed for us to emerge. The anthropic perspective adds a layer of inevitability to that rarity. Of course, we find ourselves on a rare Earth because we could not find ourselves anywhere else. A related and deeply unsettling statistical idea is the doomsday argument, which uses similar self-referential reasoning to ponder our future. It suggests that if humanity is going to survive for millions of years and colonize the galaxy, then we, as individuals, would be statistically very unusual for being born in the first few thousand years of that vast timeline. The fact that we find ourselves living so early in human history could be evidence that our long-term future is, in fact, very short. While debated, this argument shares the anthropic core. Our position in time is data, biased by our existence. So we are left with a quiet, almost tautological conclusion. The great silence is the backstory required for our existence. We do not see others because if we did, we would not be here to see them. This transforms the paradox from a scientific mystery into a logical inevitability. It suggests we may be fundamentally limited in our cosmic perspective, forever viewing the universe through a keyhole shaped exactly to the contours of our own origin. This self-referential logic, where the observer and the observation are inextricably linked, prepares us for a final, overarching synthesis of all we have explored. Perhaps the most honest answer to this profound mystery is also the most intricate. After a journey through 24 distinct possibilities, from cosmic traps to transcendent escapes, we arrive at a final, unifying perspective. The true explanation for the great silence is likely not a single, elegant solution, but a messy, layered tapestry woven from many threads we have already explored. The universe is not governed by one simple rule that silences civilizations, but by a complex interplay of filters, behaviors, and sheer cosmic circumstance. This is the 25th solution, a combination of factors, where the whole is far more effective at creating silence than any of its parts alone. We have wandered through a vast solution space, from the terrifying bottleneck of the great filter to the serene patience of Aestivation, from the predatory logic of the dark forest to the lonely rarity of a planet like Earth. Each idea offers a compelling piece of the puzzle, but perhaps each is only a piece. As SETI senior astronomer Seth Shostak has often noted, the paradox likely requires a multi-faceted explanation. We should not search for a single silver bullet, but for a constellation of reasons that together make a detectable cosmic neighbor an extraordinarily rare event. Consider a detailed synthesis. Imagine a galaxy where first, the rare Earth hypothesis holds true. Planets with the right moon, the right geology, the right star, and the right galactic location are exceedingly scarce. Life emerges on a handful of these worlds, but then it must survive its own biological adolescence. This is where a past great filter, perhaps the leap to multicellular complexity, eliminates most contenders. On the rare world that clears that hurdle, intelligence evolves. But now, the brief window of opportunity slams shut for many, as self-inflicted technological dangers, from nuclear war to environmental collapse, act as a future filter. Those few civilizations that survive this gauntlet then face the cosmic sociology of the dark forest. They learn to hide, to communicate via undetectable quantum links, or to sublimate into higher dimensions. Meanwhile, the vast, silent majority may have chosen the inward path of transcension or the patient sleep of Aestivation, leaving the physical galaxy quiet. Each of these solutions addresses a different term in the Drake equation, that formula for cosmic loneliness. The rare Earth hypothesis drastically reduces the number of suitable planets, n. Past great filter cuts the fraction of those where life appears, F sub L, and the fraction where intelligence develops, F sub I. The future filter and the dark forest shrink the average communicative lifetime, L, to a mere whisper. The choice to transcend or aestivate effectively sets L to 0 for outside observers. When you multiply these probabilities together, even if each factor is only moderately unlikely, the final product, the number of civilizations we can detect, n, can plummet to a number very close to 1 us. We can illustrate this with a simple probabilistic model. Suppose each major step, from planet formation to becoming a loud, spacefaring culture, has even a 50% chance of success. That sounds hopeful, But if there are 10 such independent steps, the overall probability of a civilization making it through all of them is 1 divided by 2 to the 10th power, or about 1 in 1024. In a galaxy of hundreds of billions of stars, that could still leave millions of civilizations. But if some of those steps are far more difficult, with success rates of 1% or even 1 in a million, the final number crashes towards 0 with startling speed. This is the power of combined modest probabilities, a perfect storm of cosmic quiet. So we are left with a reflective question. Does accepting a combination of factors make the mystery more or less satisfying? On one hand, it lacks the clean, dramatic revelation of a single answer. There is no grand villain, no universal law of predatory silence, no singular moment of cosmic transcendence. On the other hand, it feels more authentic, more aligned with the intricate, contingent reality we observe in nature and history. Great events on Earth, from the rise of life to the fall of empires, are rarely due to one cause. They are the product of converging geology, climate, biology, and chance. Why would the story of intelligence in the cosmos be any simpler? This holistic view does not diminish the mystery, it deepens it. It suggests that our loneliness, or our apparent loneliness, is the result of a breathtakingly complex sequence of cosmic, biological, and technological events. We are not just the survivors of one filter, but the beneficiaries of a long, fragile chain of cosmic fortune and survival. It also guides our search with greater wisdom. We must look not just for one type of signal, but for many types of evidence, from biosignatures on exoplanets to the waste heat of dormant megastructures, from the subtle glitches of a simulation to the quiet emptiness of a too-perfect star field. The answer, if it ever comes, may not be a single shout of hello, but a faint pattern emerging from the noise, a pattern that only makes sense when all 25 pieces of the puzzle are finally held up to the light together. This comprehensive perspective naturally leads us to a final, personal reflection on what this grand silence means, not for the universe but for us. The tapestry of 25 possibilities now lies before us, a spectrum of cosmic fate stretching from serene solitude to a crowded, hidden galaxy. This is not a menu of answers, but a map of potential realities, and our place within it demands a final, sobering synthesis. The most plausible picture of our cosmic context likely blends several of these threads into a single, daunting narrative. We may be living in a universe where the rare Earth hypothesis grants us a precious, fragile home. We may have already slipped past a past great filter, the miraculous evolution of complex consciousness, but now we stand at the precipice of a future filter of our own making, while the dark, silent forest around us suggests that broadcasting our survival could be the very thing that triggers it. This intertwined reality carries profound and immediate implications for how we conduct our search, and for the legacy we wish to leave. The debate within the scientific community about messaging extraterrestrial intelligence, METI, is a direct confrontation with these theories. On one side are researchers who argue that active, powerful transmissions are a natural extension of our curiosity, a hopeful hand extended in the dark. They believe that hiding is a posture of fear, and that a civilization advanced enough to receive our signal would also be advanced enough for peaceful intent. The other side, which includes figures like the late Stephen Hawking, issues a stark warning rooted in the darker solutions. They caution that broadcasting our coordinates is profoundly risky, akin to shouting in the dark forest. We have no idea of the motives or the nature of what might be listening. A signal could attract not a friend, but a resource hunter, a berserker probe, or a civilization following the cold logic of preemptive strike. The very silence we are trying to pierce, they argue, is the best evidence that silence is the universal survival strategy. This is not mere paranoia. It is a risk assessment based on the grimmer solutions to the paradox we have just explored. The practical path forward for SETI, therefore, leans heavily toward what is called non-transmitting search strategies. We are learning to listen more broadly, not just for radio, but for the technosignatures of cosmic engineering, for the waste heat of Dyson swarms, for the subtle anomalies that whisper of intelligence hiding in plain sight or sleeping through the eons. Beyond the practical search lies a deeper philosophical reckoning. What does this grand tapestry of silence mean for our own sense of meaning? If the rare earth and great filter solutions hold true, and we are a singular miracle, does that make us cosmically precious, the universe's one conscious eye turned upon itself? Or does it render us tragically insignificant, a fleeting spark of awareness in an endless, indifferent void? The potential for contact swings between two poles of human hope and fear. It offers the hope of cosmic community, of shared knowledge that could lift us to heights we cannot imagine. Yet it also holds the horror of existential threat, of a verdict delivered from the stars that ends our story. This duality forces us to look inward, to define what we value before we project it outward. From this synthesis, we can trace several potential paths for humanity's own future, each mirroring a solution to the silence. One path is the great inward turn, where we master virtual reality and artificial intelligence, choosing to transcend or sublimate, leaving the physical universe behind as a forgotten cradle. Another is the path of cautious expansion, where we slowly, quietly spread to other stars, perhaps cloaking our presence, becoming the hidden watchers we once feared. There is also the path of collapse, where we fail our own technological filter, joining the cosmic graveyard and leaving the silence unbroken for the next potential listener. And finally, there is the path of bold proclamation, where we decide the risk is worth the reward, and we shout our presence into the galaxy, ready to accept whatever answer comes. The true power of the Fermi paradox is that it provides no answer, only a mirror. The great silence reflects back our own hopes, our fears, and our profound uncertainty about what lies ahead. It compels us to decide not just who we are looking for, but who we wish to become. Are we a species that hides, that dreams, that builds, or that calls out? The next chapter of this story is not written in the distant stars, but here, in the choices we make with every signal we send, and with every future we strive to build on this rare and fragile pale blue dot. We have walked through a landscape of cosmic possibilities, from the terrifying to the transcendent. 25 distinct paths lead us away from the same haunting question, each offering a different reason for the quiet. Yet, as we step back from this constellation of ideas, several overarching themes emerge, binding these diverse solutions into a coherent story of our place in the cosmos. The first and perhaps most pervasive theme is the idea of the filter, a challenge so profound it stops life in its tracks. Whether this filter lies in our past, a miracle of biological luck we have already survived, or waits ominously in our future as a technological or societal trap, its shadow stretches across nearly every explanation. It is the universe's great editor, and the silence suggests its red pen is brutally efficient. Another recurring thread is the sheer diversity of what intelligence could become. We have clung to a narrow, human-centric vision of what an advanced civilization should look like, searching for radio waves and metal ships. But the solutions remind us that mind could take forms we cannot yet perceive. Post-biological entities communicating through quantum links, sublime energies merged with the fabric of spacetime, or patient Aestivators sleeping until the universe cools. Our tools are built for the neighbors we expect, not the neighbors that may actually exist. Finally, we are humbled again and again by the sheer scale of the cosmos, both in space and in time. The distances between stars are not just empty voids, they are prison walls of physics and energy. The timelines of cosmic history are so vast that civilizations may rise and fall like fireflies in the night, their brief glowing moments never overlapping. We are separated not just by light years but by millennia. The true power of the Fermi paradox, however, lies not in which answer is correct, but in the act of asking the question itself. This is not merely an astronomy puzzle, it is a mirror. When we stare into the great silence, we see reflected back our own deepest hopes and our most primal fears. We see our longing for community and our terror of predation. We see our awe at our own improbable existence and our anxiety about what comes next. The paradox forces us to define what we value, to weigh the risks of shouting into the dark against the profound loneliness of never speaking at all. It compels us to consider not just who might be out there, but who we wish to become here. The late astronomer Carl Sagan captured this duality with his characteristic elegance. He said, "The universe is a pretty big place. If it is just us, seems like an awful waste of space." That single sentence holds the entire tension of the paradox. It is a statement of both wonder and melancholy, a celebration of cosmic potential alongside the sobering possibility of cosmic solitude. It invites us to feel the weight of that silence and to decide what we will do with it. So now the conversation turns to you. After this journey through filters and forests, transcendence and traps, which solution feels the most convincing? Does the chilling logic of the dark forest resonate, or does the hopeful patience of the early bird hypothesis seem more likely? Perhaps you are drawn to the elegant efficiency of Aestivation, or the profound rarity of our own Earth. Share your thoughts in the comments below. Let us continue this exploration together. If you found this deep dive into one of science's greatest mysteries compelling, consider subscribing. We delve into the frontiers of futuristic technology, existential science, and the profound questions that shape our understanding of reality. The search for answers continues, and the next great discovery could be just one observation away. Thank you for joining this journey through the great silence.